Appreciate you being on board with us. This is Variable Speed Pressure Booster. We're going to look at it very basic and walk our way through it. We hope to accomplish these things in the next hour. Not a lot of time to do this, but we're going to work on identifying a little history of pressure boosters, and over the years, how have we provided pressure and water to a building. And we kind of like to look at domestic water pressure boosters. How do you size them? Where do you come up with the GPM? Where do you come up with the pressure? What's required? And then we see a lot of communication today in particular about hydro-pneumatic tanks. How do you size them? Where are they installed? Are they needed? And then we also want to take a quick look at variable speed versus constant speed. And last but not least, there's a new ASHRAE 90.1 2010 code out that will become code we need to look at because it's going to have a major impact on how you select and specify and buy pressure boosters. So outline of the presentation is pretty much this. We're going to start with a little historical review because I'd like to kind of see where we began. And if you start backing into history, when did the history really start on pressure boosters or on plumbing? When did we start worrying about plumbing in the world? And if you look at it realistically, it was probably 3,700 years ago. Yeah, probably that far back. I've been lucky enough to visit some of these places in the Mediterranean, and this island of Crete does exist. And this palace is there from 1700 BC, before Christ, 3,700 years ago. And this place, when they dug it up, had terracotta pipe, had a supply pipe for hot water, had a cold water supply, and a separate sewage system from 3,700 years ago. Now, that may not be the very first plumbing system. It's the very first one I've come across, and that's kind of old enough, I think, to kind of get the message out there. And I think my next favorite one is probably 1491 BC there, the next one, where we have Moses wandering around the desert. And this is right out of the Bible. You guys can go check me out on Deuteronomy if you like, but read for yourself. But I would assume this is the first latrine, the first attempt to handle sewage and the first attempt to take care of a plumbing need. And I think about 700 BC, this word plumbing came from plumbum, Latin for lead. And in case you guys have not realized this, the Romans did have supply pipe, and they did make pipe. But unfortunately, their pipe was made out of lead. And they put an awful lot of lead out in the world. And, you know, that's not healthy, as we know by the codes today. So there's a little bit of history. I've been fortunate enough to go to Rome. Some of these aqueducts are still there. It's hard to believe the Romans, in, you know, right around 52 AD, had 220 miles of aqueducts built around Rome. And listen to this. They could put 300 gallons of water into the city of Rome for every citizen every day. And what you may not realize, even way back, Rome was a huge city, hundreds of thousands of people in Rome. And they put 300 gallons of fresh water into the main city of Rome every day per person without a pump. I don't think we could do that today. I don't care how. I don't think we really could do this today. Coming on down a little bit, you go to Pompeii. Back in Italy again, where we had this big volcano that blew up, and all the lava came along, and it got captured. And again, we find the lead and the tile there, just like we talked about before. Let's jump ahead to England, about 1600. Sir Harrington did invent a water closet, as we kind of understand the water closets we have today, and gave it to Queen Elizabeth. And Queen Elizabeth was known as the clean queen because she took a bath, true fact, once a month, whether required or not. So she didn't really see much need for this thing, so it kind of went away. And a couple hundred years later, it came back out again. It was reinvented by Cummins. Then we kind of get to this modern day age, and we had come up with this term that we use in this country for water closets called a crapper. And there really was a crapper plumbing company in World War II. In fact, there was a guy named Thomas Crapper born in 1836. And this company went on until 1966. So it's kind of a personal theory of mine that the GIs, you know, in World War II, 44, 45, were in London and saw these trucks, and this is where they nicknamed it this. And then we got this preview that we used from the American West, and I think we kind of know what the outhouse was. Now, I just think this is kind of fun to kind of quickly run through this a little bit and kind of get you oriented. We're talking about water. And the problem with water is the world is covered surface with 70% of water. But the earth is running out of fresh water. With all this water out there, we're running out of fresh water. It's a precious commodity. And as you get a little older in life, you're going to see us really, really tighten down on water usage. This country, USA, has been very lucky, but even we are getting in trouble in certain parts of the country. And even particularly Georgia, take a look at it. There's been some droughts, and we've got troubles there. We're running out of fresh water. We have to maintain it and handle it properly. Now, about every seminar people see me do, I throw this slide up there. Not to insult anybody, but let's go back to fundamentals. If you're going to deal with water, you got to understand what a PSI is, what pressure is. So a fundamental building block of working with water and working with pressure is understanding that a column of water 2.31 feet high, vented at the top, requires a 1 pound of pressure at the bottom to create that. So if you go to the next column over, you got a column of water 23.1 feet high. Let's assume this is a column of water in a building 2 stories high, and it's vented. You need 10 pounds of pressure at street level just to get the water to the top of the building. And this is, I want you to begin to think about this as 1 psi of water pressure, specific gravity 1, needs 2.31 feet for the elevation. Go to a high-rise building. Let's say the building's 231 feet high. Yeah, let's call it a 20-story building, give you some idea of what that would be. We would need 100 pounds of pressure at street level just to get the water to the top of the building, just to get it up there. We're not going to do anything with it, just to fill. And I call it a fundamental building block because it's amazing how many times we blow by this fundamental thing, and we're going to keep teaching this, and I hope you will pick up on that and kind of help everybody understand a fundamental fact. So let's look a little bit of history of how we have been supplying fresh water under pressure to buildings. And let's go to roof tanks, because basically before 1945, we had to basically put a tank on the roof of a building, get it up high, and use gravity to make sure we had pressure. And as time went on, we got a little bit smarter, and we'll walk through each one of these as part of this little history lesson. But here we go. Here's a tank on the roof. Roof tank at the high point, and you note this is not a pressurized tank. It's vented. Now, air is in touch with the water here. And the very first indoor plumbing system in this country was at the Boston Tremont Hotel in about 1829. And they had a way to do a steam-driven pump, and they put this tank on the roof of the building. And they had a steam-driven pump with a little water level controller on the side, and they would pump water into the tank with a steam-driven pump. They got water at the top of the building now. Now we use gravity to downfeed throughout the building to provide water to all the water closets. Everybody had water available, washed their hands. The very first indoor plumbing systems worked quite well. Now, if you're looking at pre-48, you're looking at roof tanks, you're looking at tanks on the roofs, they work fine. But the problem is what? There's really no reliable mechanical booster system at this time. The pressure boosters do not exist yet. This was a steam-driven pump. They were not reliable systems. Pumps could fail if you had a tank on the roof and you still had water. As long as you had put water the night before to the tank, you still had it. It did not use basement space, but it did use roof space. If you had water in a tank on the roof, you had a stable building pressure. It was pretty constant. Pretty simple to operate and design. You just put water in the tank, filled it up, cut your pump off, you had water. Your tanks on the roof were vented. You would run your pumps normally off-peak. In other words, you'd have your pumps maybe running at night or when you didn't have much usage and you fill your tank up. Gave you great fire protection. In other words, if you had a fire in a building, you didn't need a fire pump. If your tank was full of water, you still had a way of managing that. So good reasons to put tanks on the roofs. Now, obviously, this day and age, we can't do that anymore. And why? You go to an architect and tell him you're going to put a 1,000-gallon tank on the roof of a building, and he'll probably laugh you out because of the weight, the pure weight. You just can't do it. So what happened next? We came along after about 48. We came along with the idea, let's pressurize the tank. Let's make it a hydro-pneumatic tank. Now, for young kids in the audience, there's no bladder here. This water is in contact with the air, and there's no bladder. That means we have to have a continuous source of air from somewhere to pressurize these tanks. So starting in the early 50s, we started having pressurized tanks. And we started putting an air compressor to them. And now the blue being the air, we can pressurize the tank with a pressure switch and cut your air compressor on and off, maintain the air, and then We used a deep well pump or some well pump to pump the water. And on the side of this, we actually use old McDonald Miller 150s. We would cycle the water level to maintain the water level. Now think about this. If we put air pressure to this thing of 100 pounds minimum, remember the previous slide, 100 pounds at 2.31 feet per pound gives us the ability to do what? Raise the water 231 feet into the air. And the tank can be where? Street level. The tank can be grade level. So the big advantages this would be between about 52 and 57 when you saw a lot of this. The tanks do not have to be on the roof. So we don't have to build a building strong enough to hold the tanks. We don't use up expensive floor space on the roof. We can put them grade level. We can put the tank in the basements. We obviously have problems with oxygen and iron and steel and corrosion. And we did have big problems with that, and they're fairly maintenance intensive because you got an air compressor, these other items to work with. Here's another picture of one showing the air compressor. And so now we got a pretty high level maintenance item to take care of just to maintain it. And again, without boring you too much, we have an air compressor taking the air in there. The air is in contact with the water. Yes, this is called a hydro-pneumatic tank. No bladder. No bladder. A lot of these systems out working today work quite well. Then we got smart. About the late 50s, we decided that maybe we could replace all of that. We could do a little value engineering. And what we did, we came along and we put two pumps together, constant speed, with a pressure-reducing valve, probably an old clay pressure-reducing valve. We could stage the pumps, and we had a package pressure booster. And that was the state-of-the-art in 57. And in about 1963, we started amp staging, flow staging, KW staging. We even started going up to 3 pumps, and we got real sophisticated. All constant speed. Worked great, ate up a lot of energy, wasted a lot of energy, but they supplied a lot of water to the buildings without any problem at all. And I'm going to give you a date of about 2007. You can argue with that date a little bit. Somewhere around that time period is when the variable speed drives got reliable enough, because this is a critical system, to begin putting on pressure boosters and really use them. And today, variable speed is the way to go. In fact, as you soon see, it's the only way to go. So it's kind of a little history in our pressure boosters and how we got here. And I think if you're going to deal with this, you kind of need to understand that. And working our way through this, we want some way to calculate or understand how much water do we need, how much pressure do we need. And I've got a typical little example here we're going to walk our way through, but we need a place to start. So let's just start off with a 100-room apartment. It's going to be a real simple, basic apartment, just so you understand. We need to calculate these from a fixed unit. And the fixed units can be converted over to GPM using the Hunter curve. But you need to understand fixed units come from code. There are plumbing codes out there that you have to follow to come up with the total fixed units required that will give you the GPM and demand. But backing up just a little bit, and here's my 100-room apartment again. Slow down just a second. Pay attention to me just a quick minute. Take the time when you're getting ready to do a pressure booster application to make a very simple, crude sketch. This is complicated enough right here. But the question to you should be, what are you trying to do? And very simply, what I'm trying to do, there's a critical fixture at the top of this 10-story building that I've got to maintain some minimum pressure on it no matter what. In this case, I'm going to say that minimum pressure is 20 pounds. You make anything you want to. I got a tank. I'm going to make it 20 pounds. That's all I need to do. So basically, it's going to be 20 pounds, and we'll go from there. Now, if you take a quick look at the 20 pounds, and that's at the very top. Let's see if I can put my way out of this. Excuse me one second. I am having a little difficulty getting the screen to close. I don't know why it came up. Here we go. I think we're okay now. Is everybody still with me? I hope I haven't lost anybody. 10 stories high, 116 feet, and I want to make sure there's 20 pounds minimum at the top. Now, I've got a pressure booster. I've got to look at city water pressure. I've got to come up with the demand. So real simple, what are you trying to do? First thing, it's very critical you maintain this. You need to go to the city and find out what that minimum pressure is going to be. If it's 40 pounds in this case, fine, and you need to write a letter Yeah, write a letter. They probably won't give you one. Ask them to send you a letter. They won't give you one. You write them a letter. You put in your file who told you the minimum city water pressure was 40 pounds. Somebody's got to take the responsibility for that. And if you're designing one, you really can't. The information has to come from somebody else. But you need to record where that 40 pounds came from. Please listen to me and do that. Keep a lot of problems out of your life. You don't want to fool with this. So taking a look at a 100-room apartment, I got 10 stories high, 10 apartments per floor. Each apartment's going to have a bathroom group and a kitchen sink. I'm going to keep it real simple. No washing machines, nothing else, just real simple. Bathroom group, faucet, water closet, and in the kitchen, same thing, sink. And that's it. City water pressure at street level, static is 55, but the minimum is 40. That means under no draw that city water pressure is 55. That's what static means. Residual or minimum city water pressure is going to be 40 pounds because when I draw the demand, the pressure drops to 40. So I've got to size my pressure booster on the 40. I have a backflow preventer and a water meter. Everybody understands we got to have those. So a real simple sketch without boring you too much is where you got to start, you got to understand what you got, and we're 10 stories tall. So here's a typical fixture count right out of the codes, the way ASHRAE put it out, I think about 1967, and every code in the country still follows these. You'll see something called a hot water fixture old and new, and a cold water fixture old and new, and you see the total count. So if I'm looking at water private flush valves or private flush tanks, in this case we're probably going to look at flush tanks, as you work your way down you see the fixture counts. Now you need to check your local codes. I suspect they use the same counts. Every plumbing engineer I talk to is still using these old fixture counts from Hunter, putting the factor on them is what they're doing. There are some new fixture counts out that are acceptable for private. The only time they're going to change is private. If you look at the very bottom of the slide, you'll see the only changes there are laboratory private, where the old was 1, the new was 0.7 at the very bottom. Now that's the total, and we're assuming the cold is 3/4 of that, so the cold is 0.75, the new is 0.5, hot water is 0.75, 3/4 of the total, new is 0.5. Not trying to confuse you, I'm trying to get you to understand in the code, under private fixtures, there is the ability to reduce the count. I'm not seeing people do that. I'm not telling you it's the right thing to do. I'm just alerting you that it's in the code. So now we got the fixture count. And with a pressure booster, we're looking for what? The total flow. Once the water gets to the apartment, they can break it down to hot and cold. I've got to have the total number of fixture units. So that's all I'm really worried about at this point in time. So where am I going to get this from? I'm going to go to the local plumbing codes, and here's some typical examples. And every state in this country is using ICC, some version of that, called IPC, International Plumbing Code. And this is just some pictures of some local codes around us in close states close by. And all of them use International Plumbing Code, and they all go back to the same fixture count I just showed you. The point I'm trying to make is the local plumbing codes rule. Chris Edmondson can't tell you what to do. You've got to go to that local plumbing code, see what they demand, and you've got to follow that code. That's the code you go by because that local plumbing inspector rules. The local plumbing inspector can demand anything they want, even if it's not in this code, because they're going to control whether you open or close your building. So don't fight it. Go ahead and get in the habit of contacting that local plumbing guy, the local plumbing code official, see what they want. Odds are it will be right out of these books, right out of what I'm teaching you. But again, remember, I don't rule, they do. That's the important lecture that you need to get from me today. If you go back to the apartments, go back to the fixture count, start taking a look. I said each apartment had in it a shower, a kitchen sink, and we're going to add them together. We're going to assume flush tanks. I would not put flush valves in a typical apartment. A flush valve takes a lot of water right up front. We're going to use flush tanks. I think that's pretty much where we need to go with this fixture count. So here we go. If I got 100 apartments, each apartment's going to take about 8 fixture units, 6 for the combination of bathroom and 2 for the kitchen. 2 for the kitchen is just a water sink in there and a faucet. In the bathroom, we got the faucet, shower, and water closet. That's 6. Add the 2 together, I got a total of 8. And again, I'm not worried about hot water this time. I'm just worried about the total fixture counts. If I got 100 apartments and 8 fixture units, that's 800 fixture units total. And where did I get the 180 GPM from? We have to go to something called a Hunter's curve, which we'll do in a few minutes to make sure you understand where it came from. But before we assume that we got the exact right amount, I want you to recognize in the real world that we live in, people are putting in full body showers. And we can argue whether they meet code or not. And in fact, there are some lawsuits going on among some cities stating they don't. We don't want to get caught in all that. But the message is we just allowed 6 fixture units total for the bathroom, 2 for the water closet. We just allowed 6 total for the bathroom. You come along and put a full body shower in it, you're going to be short of water if that's what you used. And if you're doing the plumbing design, if you're picking the pressure booster, you best know what kind of showers are going in your apartments. As to whether they're legal with the city or not, I'm not going to pick that battle. We're doing the pressure booster, right? We're sizing. We're sizing the drain, right? We got to make sure we got enough water to keep the client happy and that the full body showers may be a part of it, and you need to ask. And this is just to be interesting. Here's another one, and this is one I experienced in a hotel in Mexico recently. I call this the rain shower. 27.8 GPM of water in a shower. Look at this thing. Unbelievable. But my question is, if you are the plumbing designer, if you are providing a pressure booster, you've got to put that 27.8 GPM into your demand, or you're going to be short of water, and you're going to be in trouble. So you got to go further than the plumbing code as a message. You got to know what your client is doing, what your client's going to do with the water. And I like this one. Look at this one. This is a shower that's unbelievable. You get in that thing, I hope you don't drown in it. And the worst one I found was this, the $100,000 shower. Can you believe this? 18 shower heads, 6 zones, 65 GPM of water. Did you put that in your pressure booster? Can you afford to put it in your pressure booster? But if your client is going to be putting in these type of showers, you've got to put it in your pressure booster. By the way, it's going to take 250 gallons of water in 5 minutes. You know, I would love to be selling the water heaters to this thing. Forget about the pressure booster. But this is unbelievable. But again, if you're the plumbing designer and you're picking a pressure booster, you best ask these questions or you're going to be caught short. It's not enough to just look at the plumbing code. You've got to go to your building and dig into a little bit and see exactly what's there. There's another very common mistake we see that really, really has caused problems. Do you have a cooling tower? Is a cooling tower on the roof of your high-rise building that you're supplying a pressure booster for? Sounds like a pretty simple question, but we find a lot of times that the cooling towers are in the mechanical engineering section of the design. And I don't want to pick at anybody, but sometimes those people don't communicate to the plumbing engineer. And sometimes the plumbing engineer doesn't recognize that there's a cooling tower on the roof of the building. Now, what you got to understand is cooling towers have blowdown and makeup. And the question to you is, if you've got a cooling tower on the high point or roof of a building, how are you going to get water up there? You've got to put it into your pressure booster. Your pressure booster's got to get the water required, makeup water required, to that cooling tower on the roof. And in our world, that's in the mechanical design, not the plumbing. So you got to make sure the two people communicate. Again, know your project. Ask the question, is there a cooling tower on the roof? You want some quick numbers without digging into this too deep. If you got a 500-ton tower, I would recommend about 30 GPM. And that's based on a blowdown rate equal to the evaporation rate per the slide, which will give you 2 cycles of concentration for those guys who are on and want to really know what that means. That would give you, if you give it that much water, 30 GPM per 500 tons, and you can prorate that out, that'll get you to the point of 2 cycles of concentration. The message from this slide is this: that 30 GPM has to be where? Into the demand, added to the demand on your pressure booster. And if you don't, you're going to be short of water. And you can't be short of water. So that message out of the way, I think you kind of got that understanding. Now, on the other side of things, There's a lot of codes coming out. This is ASHRAE's 189.1, so-called green code. You see USGBC has their stamp of approval in front of this thing. They are trying, and rightfully so, to reduce the demand on these fixtures. And if you have a building that's been built per 189.1 and stamped approved, then you would be told that the fixtures in that building would follow these max demands. And these max demands would be less than the regular code that we just went through. So again, you have to understand what you're doing, and you've got to dig a little bit deeper. If it's 189.1 building, which a lot of buildings are, then these are the max water flows fixture-wise that are supposed to be in that building. But you still got to ask the question, does somebody put a body shower in there? You can't control that. But be aware, there's an attempt, rightfully so, to conserve water and to downgrade how much water we're using in buildings. So it gets to be tricky coming up with that demand. So it's just some areas you need to be aware of. So what is the required system pressure? We looked at demand and GPM. We're trying to figure out how much water we need. We're trying to make sure we don't miss anything. How much pressure do we need? What is the pressure point that we got to go to? Back to that very, very simple sketch that we talked about before, and I cannot emphasize this enough. Not complicated. Just do this. Put it down. What is the elevation? How many stories high is it? The critical fixture is going to be at the top. Is it a water closet? Is it a water tank? Is it a flush valve? What is the minimum pressure allowable at that critical fixture? What is that critical fixture? You got to do a little research. You got to ask. You got to understand what that is. How many apartments are there? Fine, but we're worried about pressure right now. Remember, 2.31 feet makes a pound. So I need that minimum pressure at the top of the critical fixture, and that's going to become very critical as we go forward for the new code bit. Then we got 10 stories of pipe, so we got the elevation. Now we also have friction. As we increase the flow through pipe, the friction goes by the square of the flow. If we double the flow, the friction goes up 4 times. Going the other way, we cut the flow in half, then the friction is 25%. So we got a piece of friction in here based on total demand in the pipe flow for pressure drop. We got a backflow preventer, we got a water meter, and we got city water. So you kind of get the idea. In this case, we're going to assume flush tanks at the top, and the flush tanks can work fine with 20 pounds of pressure at the top. So the critical pressure that we're trying to maintain under all demand loads is 20 pounds at the top. No matter what you do with the flow rate, no matter how many pumps you run, no matter what you do, you want to maintain 20 pounds at that critical fixture at the top of the building under all situations, and everybody's happy. That's what you need to understand about the pressures. So here's a little pressure booster selection procedure. And if you'll follow this, you'll stay out of trouble. I really think, I don't want anybody to get bored, but look at A. If there's anything on this whole little slide that's important to you, it's A. Go to the local authorities, ask for a flow and pressure test at the city water supply connection to your building. Ask them to give you those test results, confirm them to them in writing if they will. Probably will not put them in writing, but they'll probably give you the report. If whoever gives you the report, if they won't put it in writing, you put it in writing back, and you certify that, and you've got now the minimum pressure and minimum flows available to you at your building to design from. That is the most critical thing I can teach you, and put that in your file. If you're taking a sizing a pressure booster, put down who told you what the minimum pressure was. So I can't not make it any clearer to you. This is critical to your whole future, and a pressure booster is establishing what will be that minimum city water pressure. I've been working a lot of old-timers. I'm not going to recommend this to you, but I work with a lot of old-time plumbing guys who tell me they're going to zero. And I said, you're crazy. He says, no, Chris, over the period of time that we've been involved in this, we see the city water pressure from cities gradually deteriorating. So that's to the extreme, not a recommendation, but I just want you to be aware some of the old plumbing guys don't believe what they're being told because they've been burnt. And remember, with plumbing, you can never be short. That's part of the problem. Next part of this, obviously, is to go to state and local codes, get the 100 curves, get the fixture units, follow the codes to get you demand. This item C, we're not worried about breaking hot and cold water right now. That would be if you're worried about that part of the piping. We're just worried about total demand for the pressure booster. Item D, that simple system sketch. What are you trying to do? Where is the critical fixture? How much water pressure do you need at that critical fixture? Where is it located? Item E, we've looked at ASHRAE, looked at ASHRAE, and we looked at a B&G design manual. All three agree. And what they agree to is, how do you size the pipe? How are you going to size the pipe for your pressure booster? Because pipe size will determine the what? The water velocity at full demand and the friction loss. And that friction loss pressure-wise has to be into your pressure booster calculations. Item F, calculate the total pressure booster required in the pickups, pump, and write a spec. Now, if I take everything in this little chart that I just gave you and try to apply it, here's what you're going to get real fast. Here's a simple little chart that's been put together that we can give you a PDF on and email it to you if you like. But a lot of engineers have actually printed this thing off in color. I find it with the designers on the wall. I know all you young kids like to run computers, fine. But when you're in a fast, big hurry trying to come up with a pipe size that's acceptable to ASPE, to ASHRAE, what size can you go by? The guideline would be 5 pounds of pressure drop max at full demand. That would be the max, and that's kind of the red line across the top, the horizontal line above the yellow line, the red line. That's the 5 pounds of pressure drop per 100 feet of pipe, maximum allowable pressure for plumbing. Coming over to the right, you see a purple area, and you see 8 feet per second circled. So anything above that purple line would be 8 feet per second. So here's the magic of the chart to keep it real simple. Anything in yellow, good pipe size. Anything in purple, bad pipe size. Anything in red, bad pipe size. You're trying to pick your pipe to stay below 5 pounds per 100 feet of pressure drop and or below 8 feet per second. You follow those two guidelines, below 5 pounds of pressure drop per 100 feet and below 8 feet per second, you're going to have a good, solid pipe size for your plumbing design, acceptable design, and very reasonable, and something that ASHRAE and ASPE both will support you if you need a support. Another interesting thing this little chart is we put the Hunter curve on the bottom. In our previous apartment example, we came up with 800 fixture units. And 800 fixture units means we got to pick a pipe size, right? We got to come up with a demand. That demand is per Hunter 180 GPM, which is right off the bottom of the chart. When you see the very bottom, the 180 at the bottom, that is actually Hunter's curve with a flush tank with fixed units above it. So the bottom line is now we have a way to pick our pipe sizes. We want to stay below the 5 pounds per 100 feet max pressure drop and below 8 feet per second. People, the kids up listening to me now, understand maybe you don't like this chart. There are handheld applications now for pipe sizing. This particular one, we can tell you where it comes from. You just go online and research where you get pipe sizing, it'll pop up for you. But basically, a lot of engineers are saying, where can I get PVC pipe information? Well, it's right here in this little app. Also copper, also steel, also English, metric, and even Spanish is coming right behind it. So here's another, for you young engineers that don't want to play with color charts, you can use your little iPhone, you can pick these up, and it works quite well. So let's go back to the pressures that we need for our example. And we got to come up with the pressure required for our pressure booster. We came up with the demand with the fixture counts. Now we're trying to come up with the pressure. Remember, the critical fixture was a flush tank at the top. That's going to need 20 pounds minimum, no matter what. Remember, we had to have friction loss. Our max allowable pressure drop per 100 feet is 5 pounds. So if I look at that chart, I had about 110 feet of pipe roughly. So I'm going to say under full flow, I would not exceed 6 pounds. Maybe a little heavy with the 6 pounds, but that would be potentially my friction loss would be 6 pounds. Elevation, I was 10 stories up, 115 feet, 2.31 feet make a pound. Remember that? So I need 50 pounds of pressure at the street just to get water to the top. Then I got a backflow preventer at 12 pounds of drop, and I got a water meter at 8 pounds. So the total required pressure at the discharge would be 96 pounds. Everybody understand that? The minimum city water pressure is 40. So how much have I got to make up with the pressure booster? my pressure booster has to produce 56 pounds of pressure. Now, this is in a maybe a little hard form for you guys, but we got a little chart for you. If you take this chart along with the procedure we gave you before and just simply fill it in, you can't go wrong. It's kind of a check-off. Doesn't matter whose pressure booster you're doing or what, you got to deal with these issues. And basically, I'm suggesting you put this in your file. You kids can make a scan and scan it into your file electronically. I don't care how you do it, but you need some record of how you came up with the total GPM and the total pressure required for your pressure booster. So very simple here. If you walk away through it, we start off with the fixture units, 100 demand curve to get the GPM. So you got a record of that. You got it sitting there. Then you walk your way through. First thing, obviously, where is that critical fixture? What is it? Is it a tank? Is it a valve? You got to have that number. You got your friction, your elevation, pressure drop through a water heater. If you have a reducing valve or check valve, a backflow, whatever you got. If you walk through this, you'll come up with exactly the pressure that you need, and you can throw it in your file, and you're there. And very quickly, I don't want to bore you with this, but as an old guy who's been in this business way too long, I see things. And here's this 100-room apartment example that we just talked about. And in red, I just popped in all the numbers we talked about, 800 fixed units from 100, 180 GPM demand, came through all those pressures we talked about. And now you got a permanent record of what you did and why, and then you know the numbers. And my pressure booster needs to be what? 180 GPM with a boost of 56 pounds. So now you have a record. You know how you got there. What do we do next? Well, next we're going to talk about hydro-pneumatic tanks a little bit. We've come up with our pressure booster. We've come up with the GPM of demand. Now we got to apply that a little bit. Let's go a little bit more into the system, and let's see where we're going. Now, the first hydro-pneumatic tanks did not have a bladder. Now, all you kids in the room and all you kids listening to me now, we say hydro-pneumatic tank today, we're thinking about bladder tanks. We pre-charge the tank, it's there. So the question comes, on a variable speed and or a constant speed pressure booster, do you need a hydro-pneumatic tank? And the answer is very simply yes, you got to have it for drawdown. Water is non-compressible. So in order to keep from having short cycling, you need a hydro-pneumatic tank on every pressure booster application so that when you cut the system off on pressure, you can handle flushing a water closet or taking a glass of water or something without having to turn the pressure booster back on. So the reason for the hydro-pneumatic tank is to stop short cycle. The reason for the hydro-pneumatic tank is to prevent the booster pump from short cycle. Just that simple. This is what they look like. You got a charging tank on a charging valve, and we're going to talk about charging pressures a little bit further down the road, but they do need to be factory charged. Need to be charged in the field to the pressure required. And basically, here's a little example of what we're talking about. Booster system, a couple pumps, and typically these would be on the discharge headers of the pressure booster. Could be at the high point, but we see most of them close to the discharge headers of the pressure booster. And we see probably a check valve between us and the pressure booster, hydro-pneumatic tank, and typical piping. And what we're trying to accomplish is to be able to turn that pressure booster totally off for some period of time, especially at night, and not running. And that way we can save a lot of energy and have the hydro-pneumatic tank maintain the pressure for us so we don't have a problem with water being non-compressible. So how do we do that? How do we size it? Let's take a quick look. This is critical, I believe, to the proper application of pressure boosters. That's why this has been discussed. Now, the whole idea, again, is to provide drawdown between an on and off pressure to stop short cycling, to save energy, How do we size a hydro-pneumatic tank? A couple things that you're going to have to answer. First question is, question one, how long would you like the pumps to be off at no flow? In other words, you're saying, I've got a typical building here. The most efficient pump in the world is what? A pump off. The most efficient pump in the world is a pump off. Can't beat it. So how long can I keep it off? Well, that's going to be some factors based on the kind of building you're in, kind of usage you're in, and how long do you want to try to tempt it off. You don't want a leaking faucet to make a pressure booster pop on and off. That's nuts. Also, the tank location becomes critical. Is it going to be on the discharge head of the pressure booster, which is the most common, or is it going to be located at the top of the system, which will give you the smallest tank? And real quick, to give you an example, the most efficient place would be top of the system, which is probably the most expensive place to put it. And a lot of people like to just go ahead and put them on the discharge side of the pressure booster and be done with it. So let's walk through those two typical examples and show you the difference in size of a typical tank. So real fast, and just make sure you kind of got the idea. Back to my pressure booster again. Let's assume in this case I have a pressure booster size for 124 GPM with a 58-pound booster. And I've got this particular setup, and I'm going to put the Hydro-Pneumatic tank, the bladder tank, on the discharge of the pressure booster or at the top. Which size, what size do I need? How do I size my Hydro-Pneumatic tank? Now let's get something across to you, and you're going to be seeing more of this in a few minutes. The new ASHRAE energy codes basically ban PRVs. PRVs are gone. Constant speed's dead. We'll talk about more in a minute. So I'm going to eliminate the pressure reducing valve. I'm going to exit out and say it's not even there. So I'll probably have a check valve there. And I'm going to have a tank sitting there at the discharge of the pressure booster in the equipment room at the same elevation as my pressure booster. Let's assume that's what we're doing. Well, in this case, my pressure booster is boosting up 58 pounds, but I got street pressure of 40 pounds. So when I go to look at the discharge pressure of my pressure booster under full demand, I'm at about 98 pounds. Now, a lot of people in the world never have lived in the country where you have a hydro-pneumatic tank or well pump. Those of you that are listening to me already know this. You have to have a pressure differential to keep from cycling a pump to death. So if you live in a country with a well, you already know you got a hydro-pneumatic tank on your well pump. You already know you're probably turning that pump on at about 30 pounds. You're pumping up to 40 to 45 pounds and cutting off. This big tank sitting there. So that pump doesn't go bam, 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 bam. You don't want that going on. So you guys that live in a country who've had experience would already know how these things work. This is no different than this pressure booster. We have to have some minimum differential pressure to work with to make this work properly. And if you're taking a shower with 30 pounds versus 45 pounds on a properly sized hydro-pneumatic tank, you'll know the difference. You guys that live in the country, you don't even worry about it. Just such a gradual change is not a big deal. So in this case, a variable speed pressure booster, before it turns off, is going to be to 98 pounds. When it runs 98 pounds and no flow, there's a way to cut them off. We basically do it on heat sensing because we're deadheading, building up heat inside the pressure booster, and we cut it off. But we cut off at 98 pounds. At that point, we want this tank pressurized. When do we turn the pressure booster back on? When do we tell the system to turn the pressure booster back on? When the pressure drops to 88 pounds, in this case, or a 10-pound drop, we're saying turn the pressure booster back on. So the differential pressures are, at cutoff, we're going to have 98 pounds of pressure on the 100-gallon tank, on that bladder tank. We're going to cut it back on 88 pounds. We got 10 pounds of differential. Now, how much water do we need to put in that tank? So we got the differential established. We got 10 pounds of differential. We said it's fine. That's how we're going to use it. How much water do we need to put in the tank? Well, what kind of building do you have? And there's a chart that we can make available to you, and because the message we're trying to get across is that one size bladder tank does not fit all. If you're in a hotel, the demand is entirely different than a prison. If you're in an apartment building, the demand is entirely different than a hospital or a school. So we're saying to you, how long do you want it off? How many minutes do you want it off at night? And this is based on a typical demand load profile of these types of buildings and the total GPM. And this chart is based on you being down 30, let's not use the word down, being off 30 minutes at night, or 30 minutes at shutdown at night on the low draw. Based on the total GPM demand left-hand column, the type of building will give you the gallons of water that you need to put into that bladder tank between 98 and 88 pounds, called the acceptance volume. How much water do I put in that bladder tank between on and off, so that typically I would be offline 30 minutes at night. Now, if I had an apartment building at 124 GPM, and I think you can see the column here, 50 GPM and 100 and 150. So if I kind of interpolate between those two, 124 GPM, an apartment building, I want to be off 30 minutes. then basically I'm winding up around 19 gallons of water I need to put into my bladder tank between on and off to be offline 30 minutes at night. Now, if I was in a hospital, you see it's a huge difference. Think about it. You know, hospitals at night don't really shut down. They keep going. So the message is, with a hospital, I need a much bigger bladder tank than with an apartment. So my message to you very simply is, one size bladder tank does not fit all applications. You need to ask that question. So I need 19 gallons of acceptance volume for an apartment to be offline, 30 gallons. So let's take that and put it in this little chart to come up with how many gallons of water do I need to put into the bladder tank between on and off. Well, basically, 19 gallons gives me 30 minutes, right? So let's assume I want to be down 15 minutes. I want to shut it off 15 minutes at night. So it's half of that. So I need 9.5 gallons acceptance volume. That's all I need to put in my tank between 88 and 98 pounds, 10-pound differential, to come up with the size tank I need. So if I go to the typical tank size chart, Hydro-Pneumatic tank, 88 pounds, and I work on my acceptance volume, you come up with a 0.087. It's acceptance volume, and you need a 109-gallon tank. There's been a lot of detail on this, but you guys need to slow down and understand this a little bit. So basically, here's the same chart if I put the tank at the top, and all I'm trying to do is get across to you the acceptance volume. I said the 88 pounds was initial pressure, 98 was the max, so I got a 10-pound differential in my table. This is about as close as I can get, so my factor is 0.087. If I take a look at putting the tank at the top, then my acceptance volume is going to be same tank. I got to put 10 gallons in it, but my initial pressures are different, 43 and 33 up here at the top, and I wind up with a 57-gallon tank required. So the message is, by putting the tank at the top, it can be smaller, the pressures are different, and I still can take advantage of the Hydro-Pneumatic tank. I believe what you're going to find most commonly, it will be put at the bottom on the discharge header and not at the top. And that acceptance volume, those tank charts are very simple to follow, and you just kind of come up with that. Now, here's a tank at the high point again we just talked about at 57 gallons. Same 19 gallons of storage required, 15 minutes, 9.5 gallons is what we need to put in for just 15 minutes, being off 15 minutes. And you see the initial pressures are different. We start off at the discharge header located at 98 pounds. But remember now, if I put the tank at top, what have I done? I've taken out the friction, and I've taken out the elevation, right? And the pressures at the top would only be 43 pounds, where if I put the Hydro-Pneumatic tank at the top, it's going to see 43 pounds at cutoff. And again, if I go back down to the bottom, the Hydro-Pneumatic tank at the bottom, I needed 88 pounds to cut it back on. But when I cut the pump back on, how much pressure would be at the top? I take the 55 pounds of friction off, the elevation off, and at the top, I only need 33 pounds at the top. So my initial pressure, if I put the tank at the top, is 33. Final pressure is 43. Still got the 10 pounds of differential between on and off. But look at my drawdown coefficient. It's now 0.168. To make a long story short, your tank size is about half. I'm down to 57 gallons, performing the same thing. Enough said on Hydro-Pneumatic tanks. Just want to kind of get the message across to you. And one other little quick comment that the old plumbers have taught me that you ought to pass on to those people as you talk. What pre-charge pressure do you want? If you're at the discharge of the pressure booster, the initial pressure is going to be 88. We're going to suggest you pre-charge to 78. If you're at the top, put your Hydro-Pneumatic tank at the top, we would suggest you pre-charge to 23. The reason for that is very simple. If you take your drawdown tank and take all the water out of the tank before you turn your pressure booster on, water is non-compressible. You're going to get a sudden drop in pressure. So the old plumbers are telling me they do this to make sure they don't get that sudden drop. In other words, if you pre-charge the 88 pounds on the tank at the discharge of the pressure booster, then are you sure, are you positive that your pressure booster is going to come back on before you fall below the 88 pounds? If you miss that just a little bit, water being non-compressible, you're going to have a sudden drop in pressure. So what the guys are telling me to do is pre-charge them to 78. That way your pressure booster come back on before you draw all the water out of the tank, and you won't get that sudden drop in pressure. Bottom line, if you're an engineer listening to me, you need to put that pre-charge pressure on your drawings, because that tank has to be pre-charged before you hook it to the system to work properly. Hydro-pneumatic tanks, new codes, ICC says that you've got to have ASME relief valves on. You got to make sure you do relieve the pressure. You got to put one on there. So when you go looking at a typical pressure booster system, you're going to have two hydro-pneumatic tanks. You're going to have one for thermal expansion for the water heater. You're going to have one for the pressure booster, and the pressure booster has to have a pressure relief valve on to meet code. But yes, there will be two tanks, one for the water heat expansion and one to cut the pressure booster on and off. So let's look a little bit quickly at constant versus variable speed pressure boosters. Why are we saying variable speed is the way to go? Well, you've got this new standard now, ASHRAE 90.1 2010. And take a quick look, and this is critical that you see this because a lot of engineers are not aware of this yet. In fact, I would say most of you are not aware of this yet. This is a mandatory provision in ASHRAE 90.1 2010 that we're going to have to follow. And what is the center item A? Sensors shall either be located near the critical fixture. I hope I've taught you where the critical fixture is at the high point, or logic located to do the same to simulate it being at the critical fixture. In other words, they would like for you to put the sensor up at the high point of the building, and you're going to run a hard wire all the way back to the pressure booster. I don't see anybody doing that, but that's what the mandatory provision says, or logic that does the same. Item B, no device shall be installed directly on the pressure booster for reducing pressure. In other words, pressure reducing valves are dead. You can no longer legally put a pressure reducing valve on the discharge of a pressure booster. In my humble opinion, you just kill constant speed pressure boosters. You've got to go to variable speed. If you don't, you're going to kill yourself. You can't do it any other way. You're now going to have to go to variable speed. I say that kills constant speed pressure boosters. Item C, no booster system shall run and no flow. In other words, you're going to have a hydro-pneumatic tank. Can you make a pressure booster run without a hydro-pneumatic tank and cut off? Sure you can. But water's non-compressible. So you got a pressure booster in a hotel, and you got no hydro-pneumatic tank. I go get a glass of water after you cut it off. It's going to cut back off. Crazy. You got to have a hydro-pneumatic tank. That's what that means. Constant speed pressure boosters using pressure reducing valves, October the 18th, 2013. That's this year, ladies and gentlemen. Constant speed is dead. It is the law. I'm sorry, that's the message you better get. It's the law. You're not going to change it. Along with this message, I think you need to pick up on this. We're also saying to you, you don't want across-the-line constant speed bypasses on your variable speed drives. If you put across-the-line constant speed bypass on your variable speed drive, and your variable speed dies, and you run at constant speed, you don't have a pressure reducing valve, you're going to blow fixtures off the wall. You can't do that anymore. So you want variable speed drives, no across-the-line constant speed bypasses, because you do, you're going to get in trouble. That's the law. That's what's coming. So why is this happening? Why would DOE make such a ruling? Why would this be coming down the road? Very simple. Pressure boosters are oversized. We just went through all of that. You got these big showers. You got these fixture counts. You got the Hunter curves. It's a guess. It's an estimate. Who knows what the real demand may be? We got Hunter curve that we went at. Remember, we had the 180 GPM get a demand. The Hunter curve information came out of ASHRAE in 1967. It's old stuff. Nothing wrong with it, but it's very conservative. We're going to have way too much water required. Do we have variable head loss? Sure we do. We got that 5 pounds of friction loss per 100 feet max. As we vary the flow, the friction loss varies. So that's why they want you to put it at the remote sensor. That's why they want you to control out there, so you can take advantage of that and run your pumps even slower. And we'll give you some numbers on that and give you a detailed example in just a few minutes. Pressure reducing valves. Yeah, pressure reducing valves on constant speed pumps work great, but they take 5 to 8 pounds of pressure just to put one on there. 5 to 8 pounds of pressure is a lot of kW, a lot of energy that we're wasting. So what did DOE do? What did ASHRAE 90.1 2010 do? They are banned. You can no longer put them on a pressure booster. Do our loads change? Sure. Here's a typical load profile of a complex. Look at here. In the morning at 12 a.m., the GPM is very low. Look at it peaks when about 225 GPM around 7 o'clock. Everybody's taking showers, kitchen's on, dishwasher's running, whatever. And at night it drops back down to that 20 GPM. So why would you run a pump constant speed, which has got to be sized to do this peak demand at this time of day? So we certainly can take advantage of the flow changes in a typical load profile. And this is probably typical for your house. Do suction pressures change? Absolutely. Those of you who live in a city, hope we're paying attention to this. City water suction pressures change over a period of time. They will gradually probably go down, which is happening in Atlanta a lot right now. They're actually deteriorating as they add on more and more demand. But in a typical situation, you've got this friction thing going on. So during the day, they will actually change. So let's take a quick look at a pressure booster situation that could be constant or variable and give you some ideas of why you have your sensor location, where you put your sensors, and why we're saying variable speed is the way to go, that ASHRAE is correct. There's no other way that really makes any good sense. Let's take a quick look at this. We got a demand here of 400 GPM. You see the pressures involved on this. And the point I'm trying to get across to you, should that pressure booster be constant or should it be variable? Which way do you think makes the most sense and why? So let's take a quick look at this. Now here's a variable speed setup with a critical fixture at the top. Remember we said the critical fixture would always be at the top. And ASHRAE is telling you they want you to sense up here at the top that critical fixture and control the speed of the pressure booster from that critical fixture because they know that's the most efficient place we can run this variable speed at the lowest speed we can on the pressure booster to do this. Now the things you need to understand, look at this chart real quick, and we don't have a lot of time as usual, is in red up here we have 20 pounds of friction loss between the discharge of the pressure booster all the way to the top where that remote fixture is. So there's 20 pounds of friction loss. And real simple, to get this in your head real simple, that 20 pounds of friction loss only happens when? Under a full flow of 400 GPM. So at 400 GPM is the only time that we would have 20 pounds of friction loss, right? So if I'm at 200 GPM, this thing becomes what? 5 pounds. If I'm at 100 GPM, this thing becomes what? 1 pound. If I'm down to 50 GPM on no flow, what is the friction loss? 0. So by running and controlling the pressure booster from the remote sensor, I'm able to run slower because I can see that 20 pounds of friction loss. If I ran it from a local sensor on the discharge of the pressure booster, I always have to assume the 20 pounds is there because I can't see it. Now at a high level, that's kind of what's happening here. I kind of want you to understand that, making sure you got that in your head. Let's back up and make sure you understand if I put pressure reducing valves on this, how bad it would it be? And for you engineers in the audience, here's a typical little curve that kind of explains that to you. What am I trying to do? I've got 20 pounds of suction pressure. I'm trying to boost it 54 pounds. I got a boost pressure I got to maintain. So the solid black line across the top is the pressure I have to maintain to keep everybody happy. This little pink line is my efficiency curve. Across the blue line is my pump curve. If I'm constant speed, no PRV, constant speed, no pressure, no variable speed pressure drive alive, I'm using constant speed with a pressure reducing valve, in this case a 4-inch PRV valve. Everything in yellow is wasted energy. In other words, at small flows here, my pressure reducing valve is choking the pump down to maintain this 74 pounds discharge pressure I got to have. So everything in yellow is wasted energy. It's like driving a car with one foot on the accelerator and one foot on the brake. It's stupid, just plain stupid to do that. So for that reason, DOE, ASHRAE has banned pressure reducing valves. You cannot do this anymore. You can't do that. So now we've got to have a variable speed drive to hold that solid black line there, whatever pressure you want to maintain. So the yellow, they have banned. The PRVs, they have banned because of all the energy that's been thrown away at that point. So I hope you understand now why constant speed PRVs are banned. They want to get rid of that. They want to get the system more efficient. So let's go back and take a look at, again, a little bit at this pressure sensor location, which is the next tricky part that you've got to catch on. What should be the set point for your variable speed pressure booster? What pressure are you trying to maintain? If you put your sensor at the critical fixture, and I think we've taught you where the critical fixture is. It's going to be at the high point, and you set that to be your minimum pressure for your set point. That becomes your residual pressure. And that's what ASHRAE, that's what DOE is asking you to do. In this case, 30 pounds. So I need 30 pounds at the high point to maintain that pressure at all times. So backing up again, looking at my chart, I'm saying if I look at a critical fixture at the top, I want to maintain the pressure at 30 pounds no matter what. I'm going to control my variable speed pressure boost accordingly to always maintain 30 pounds. Why would that be going on? What is the results of doing that versus taking the local pressure of here? If I had to go to local pressure, then I've got to maintain what? 74 pounds all the time because I can't see the 20. I only got one set point. So if I set this for 74 pounds, it works fine. But I don't have any visibility of the flow. I do not know what the flow rate is, and I cannot see this 20 pounds of friction loss that I want to get rid of because my pump will run slower. Let's give you a concrete example of that. It's kind of hard to see sometimes, understand it all, but let's just make sure you understand the numbers a little bit. If I had a remote sensor at 30 pounds versus a local sensor at 74, what happens to my speed change? We work math all day long, but this is what you come up with. If I use a local sensor right here, I get a 10 pounds speed reduction. If I use a remote sensor, I get a 26% speed reduction. Speed reduction local sensor 10%, speed reduction remote sensor 26%. You're saying, Chris, that doesn't sound like a whole lot of money, but we're working with a cube here. We got a cube factor. If I can take the RPM, I can cube it out to get my horsepower. So this becomes a huge difference in savings that we can apply. So here's a typical example, a little simple example. 2 pumps, constant speed, very cheap energy, 6 cents a kilowatt hour, $6,700 a year. I put 2 pumps in variable speed with a local sensor. I save a lot of money. I save $3,500. Great. I did a good job, and you did do a good job by going to variable speed. This is why variable speed versus constant speed is a no-brainer. You've got to do it. You can't continue throwing that kind of money away. So you've got to go to variable speed, period. But how about going from the local sensor to the remote sensor? That's the next piece that nobody's really doing right now. Why did DOE say you got to go to the remote sensor? You saved another $1,000 at 6 cents a kilowatt hour by simply changing the sensor location. And that's forever. Makes good sense to me. You start working the numbers out. By the way, you start looking at codes, and everybody around you, here's Duke Power, happens to be typical where we are. You can get a savings from Duke Power by energy rebate. They'll actually pay you to put a variable speed drive in. You can get online and check this out. I think it's worth looking. Wherever you may be in the country, check your utilities out. They are paying you to put variable speed drives in. Back to ASHRAE 90.1 2010 to kind of wrap this up for you to make sure you got the message. DOE has said that by October the 18th, 2013, you have to put a code in place in every state that will equal ASHRAE 90.1 2010. If you don't want to do that, you can apply to an extension, but you've got to go ahead and begin to do it. Here's the mandatory provisions, a repeat of an earlier slide you saw, impacting pressure boosters. You've got to have a remote sensor at the critical fixture or the logic that does the same. You can no longer use a pressure reducing valve, so what does that mean? Variable speed is here to stay. And no booster shall run if there's no flow. So now you got to have a Hydro-Pneumatic tank sized properly, and we gave you some ground lines for that, I hope. Bottom line is the law says what? The law is going to become per DOE ASHRAE 90.1 2010. You're going to have remote sensors at the critical fixture or logic, and you're going to have a pressure booster to do it. I'm assuming you people on the phone here would like to not break the law. That's the message to you. That's the whole idea of the concept of what we're trying to do in this webinar, is get you to understand the changes. Thank you for your time. It's been fun. Appreciate it. If you got any questions, send me an email or something, and I'll be happy to try to respond to you. Have a great day. Any questions from anybody?
Okay. And that brings it to an end. I want to unmute everybody. If somebody wants to hang on,
I think we
answer any questions.
I'm still getting used to this.